Hi, Mr. T here. In this video, we're going to look at the Doppler effect and how its acceleration impacts on it. So this is, if you haven't watched my first video on Doppler effect, I'd recommend that you stop now, go and watch that before we come to this one, because the concepts in here add on from the previous ones. So when we talk about acceleration, there are two types of acceleration that we might be expected to know about. The first one is circular motion. So in this case, we have a source, which is a toy aeroplane moving around a circular path, and its velocity is acting tangent to the circular path and is constantly changing. In order to change the velocity, we need to have a force, just a second, and going towards the center. And because we have a force towards the center, this object with mass is accelerating towards the center, has a centripetal acceleration. Now, in order to observe the Doppler effect, the aeroplane needs to be producing a sound that the observer can hear, in this case 450 Hertz. Now, it doesn't need to be the source that is moving in a circular path. If the source was standing still and the observer was moving in a circular path, we would also notice an effect on a Doppler effect because of this acceleration. So let's look at specific points in this journey. Point 1. Okay, so when we're at point A here, we can see that the instantaneous velocity that's acting at a tangent to the path is going directly towards the observer. That means we have the source moving directly towards the observer. The source is catching up with the wavefronts that it's emitting. So therefore, the wavefronts are becoming closer together. Therefore, the wavelength is decreasing. And because we know that our frequency is inversely proportional to our wavelength, and our wavelength is decreasing, our frequency must increase. Because the speed of the sound through the medium stays constant. So this is the point where it's moving the most towards the observer. So there's another point where we have a maximum Doppler effect, and that's at this point here. That's at point C. Now you can see at point C, it's moving directly away from the observer. So our velocity vector is in parallel or in line with the observer in the direction it's moving. In this case, because the source is moving away from the observer, it's moving away from the wavefronts. They're going towards the observer, and the wavefronts spread out. The wavelength increases, and remember again, because the frequency is inversely proportional to the wavelength, as the wavelength increases, the frequency decreases. So at this point, we hear a lower sound, and at A, we hear a higher sound. Sorry, a higher sound, I mean a higher pitch at A and a lower pitch at C. Higher frequency equals higher pitch, lower frequency, lower pitch. Okay, then we have point B, in between both. At point B, the aeroplane is moving perpendicular to the observer. There is no component of that velocity vector that is acting either towards or away from the observer. Therefore, there is no Doppler effect, and the frequency heard is equal to the frequency that the plane emits. Actually, at this point here, this is another point B. The velocity vector here is another point in the circular path where it is moving exactly perpendicular to the observer. So if we look at these three situations here, we can say that the frequency of A is higher than the emitted frequency. The frequency of B, remember, which is also over here, is equal to the emitted frequency, and the frequency at C is lower than the emitted frequency. So now we've labeled the frequencies on this diagram, we can explain how the frequencies change as the object moves around the diagram. And this is usually the type of problem that they ask us, the type of question. So let's have a look. So here are some questions they might ask. A model aeroplane travels in a circular path at a velocity of 20 meters per second, emitting a constant pitch of 4,500 hertz. Calculate the minimum and the maximum frequencies. So what we're using here is the Doppler equation to find the maximum frequency. That's when the plane is going directly towards the observer. So it's the VW minus VS equation. And we carry out that calculation here, and we find out that our frequency, let me just put the equation up here just so you remember it. Remember, the equation is F dash equals F VW over VW over minus VS. Now remember, it's plus or minus, but in this case, we're using, I'll put it like that, it can be plus or minus. In this case, we're using minus because they're going towards and it's the highest frequency. So we can work that out. We can work out the minimum frequency or the lowest frequency by using the addition on the denominator. And we get 425 Hertz. So the frequency at its maximum is 478 Hertz and its minimum is 425 Hertz. Second question, label the points X and Y on the path. So here we're identifying where the position, X is the position where the observer hears the lowest frequency. So lowest, remember, is when the aeroplane is moving away from the observer. So we need to look at the observer and look which part of the path is tangent to the observer. So we've got two tangents, this one here to the observer, and we've also got here. But if we look at our aeroplane, it's moving around in this direction. Yep. So in this case, it's moving towards. So this is the higher pitch. In this case, at this tangent, it's moving away. This is the lowest pitch. So X is the lowest frequency or lowest pitch here, and Y is the highest pitch. Here we go. Describe how the observed pitch would change as the aeroplane moves from A to B. So A is lowest and B is highest. So it would start, if we can imagine the lowest pitch, and then it goes higher. Okay, that was a really bad sound, but you can imagine what's happening is it's a lower pitch, and then goes to the point in the middle here where it's the exact pitch that the aeroplane produces, and then it goes to the higher pitch over here. So we just need to explain that clearly. So we say something like this. At point A, the observed frequency is lower because it's moving away. At point B, it's higher because it's moving towards. As we go from A to B, the pitch will increase because it's going from lower to higher. And that's a really common type of question they'll ask you when they're talking about acceleration and the Doppler effect. Okay, the second type of problem is acceleration in a straight line. So here we have a car starting from 0 meters per second and going up to 10 meters per second at C. It's been constantly accelerating. It has its horn on at 140 Hertz. So what would we observe? Well, you can think about it here. I guess the easiest way to think about what is the frequency at the start? It's 140 Hertz. Yep, because here we have Vs, so we have F equals F dash because it's not moving. And here we have the frequency is at the maximum. So this is a lower frequency and higher frequency. So we'll see an increase in frequency. So it's very much just breaking down the diagram, putting some notes on it, and thinking clearly how the frequency changes. So at point A, 0, we could say at B, the frequency observed is larger than the frequency, and C, obviously, it's even larger still. Therefore, over the course of this journey, as the car accelerates towards the observer will hear a pitch of increasing frequency. Okay, so we're going to get a pitch getting higher. And these are the two types of questions that they might ask you to solve or to carry out when you're talking about acceleration to do with the Doppler effect. Okay, hope this has been helpful. Look, make sure you subscribe to this video, then you'll get updates when I upload new videos about how to solve physics problems. Cheers.